When a body is subjected to loads, when a body is subjected or displaced, to the body are imparted to the body. That is, work is done. That is, work is done. If the strains imposed, if the strains imposed are within elastic limit, the strain stored in the body is recoverable loads are removed to restore the body the energy stored due to strains of an elastic type of an elastic type is known as strain energy. Strain energy concept used to determine the displacements of joints, the displacements of joints are supports. I will get back to all these points once again. Please note all the points first. Strain energy concept in structural analysis can be used to determine the displacements of joints or supports. There are three methods that are available where the strain energy concept is used to determine the displacements of joints. First method is real work or strain energy method. Unit load method. direct load method. Third one is Castigliano's method. Castigliano's method. So just listen once again. What we said is when a body is subjected to certain loads, then structure the body, whatever, for example, consider an object is there. This object is being subjected to certain external loads. When it is being subjected to certain external loads, then what happens? Definitely the body will undergo certain deformations. So if you consider this is the deformed shape of the body, something like that, due to the application of the loads, it will deform like this. And at each load, it will undergo certain deflection that we call it as delta. If a load of P1 is applied, the corresponding deflection is delta 1. Corresponding deflection is delta 1. What we will observe is due to this application of the loads, when a deflection is applied undergone, if you remove the load, then it will go back to its original position if it is within the elastic limit. So here I am calling it as strain. So strain is nothing but the change in length by original length. So here the deflection is happening. So the displacement is happening. Displacement by original dimension, that is corresponding to the strain. So within the elastic limit, when you remove the loads, then this member or the body is recoverable. It will go back to its original position. It means that when the loads are removed, the energy stored is used to restore the body to its original position. Whatever that is stored in the body to restore to its original position, that is considered as strain energy. The member or the body is undergone to certain strain energy due to the application of the external loads. And when you remove them within the elastic limit, if the loads applied are within the elastic limit, and when you remove them, then it will go back to its original position. The energy stored due to the strains of this elastic type, we refer them as strain energy. In our structural analysis, we are using this concept to determine the displacement of the joints or the supports for in-jointed frames as well as rigid jointed frames. So this strain energy concept is being and the third one is Castigliano's. So the concept is nothing but here when you apply any load, then the body will be subjected to deformation. And this deformation can be regained to its original position when you remove the load. If loads are within the elastic limit, when the loads are like when the strains are crossing the elastic limit, then if you remove the load also, it will not regain to its original position, and that we call it as plastic state. So we have elastic state as well as plastic state. So something like take it will get deformations. Now just remove that one. What happens? it will regain to its original position. While you are pressing it, as it is undergone to its certain deformations, certain energy is stored to get back. Whatever the energy that is stored, we refer it as strain energy. Here, understand the point as displacement. When I am referring it as displacement, how we will use this strain energy in our bars, as well as we will see for axial loading. For a bar, if you try to extend the bar, if you apply a tension on the bar, then what is the strain energy that is stored? We will derive an expression for the strain energy stored in a bar for axial loading as well as for a beam for flexure loading. Keep side heading. Strain energy due to axial loading or direct force. Yes. So we are discussing regarding the strain energy due to axial loading or direct force. Now, a bar of length that this is axial loading along the length of the member it is acting, and the length is L, and it is having certain cross section, and the cross section is nothing but cross sectional area is capital A. What we are doing is we just consider a graph along deflection versus loading, deflection delta versus load P. Now what actually happens here at zero load, zero deflection. But as you keep on increasing the load here along y direction, the deflection will also increase. When you keep on increasing the load, then this is the graph that is obtained for load versus deflection. For load versus deflection, the graph is P to delta. If you draw a graph for load versus deflection, then this is the graph. Now, in this is the value of P, and corresponding deflection is nothing but delta. So corresponding deflection is nothing but, for example, if I want to know what is the deflection at certain point corresponding to a load, then you can using this graph you can calculate. But P corresponding deflection is nothing but delta. The graph is showing the relationship between the relationship between the load action for a bar subjected to axial loading. Yes, 137. Any doubt, Ma? You raised your hand. Just if you want to repeat once again, I am repeating. So the thing is nothing but we are considering a bar which is having of length L, and gradually we are applying a load from 0 to P. When you gradually apply a load from 0 to P, then at P the deflection value is delta. If you slightly increase the load, then what happens? This will also increase. That means if there is an increment in the load by delta P, if this value is delta P, then the increase in the deflection is also, this is also delta, or we can refer it as Px. So just instead of corresponding to a load of P from here to here, this is P, there is the value is P here. Now for a slight increment of load delta P, the increase in the deflection is nothing but Dx. Now, here whatever the force we have considered, here I have just drawn this as tension. The same can also be applicable for compressive loading. The same can also be applicable for compressive loading. So right on the point, the force can be compression or tension. The force can be compression or tension. Now, what is the external work that is done here? Just understand, when a load is applied externally, we can calculate it as, you know, that the work is nothing but load into deflection. From our basic physics, we have learned this one, right? Now, here I can write down this as work is nothing but force load into deflection or force into displacement. Your x is nothing but here deflection or displacement, you can refer. Now, external work done is equal to work done is equal to, here see, just replace this with x for our simplicity, just to make it as x, deflection x. Now the load applied is P and the corresponding x. So now why? Because here just if you draw a graph corresponding P versus is load versus deflection, the graph is moving like this. So this value is P and corresponding this deflection is X. Now we have to consider this is the headed portion. And the work done is nothing but area of this hatched portion. Area of this hatched portion. It looks like a triangle. So the area of this one is nothing but half E into X. The area of this one is nothing but external work done is equal to half P into X. In general, you may know that we have to consider P into X. But why we are writing it as half into P into X? So when you are externally applying a load, corresponding deflection is nothing but X. Now, what happens here? When a body is subjected to certain deflection, it will be having energy. So you can equal the internal strain energy is equal to the external work done. Write down that one. So the external work done is external work done is equal to the internal strain energy to the internal strain energy. So internal strain energy we are calling it as U. This is equal to the strength of materials if a bar is subjected to any deflection. So certain deflection x, if x is a, this is L is the original length, x is a change of x is equal to PL by AE. Do you remember this or not? So we know that where stress is nothing but load by area. Strain is nothing but change in length by this is P into L by x into A, which is E. I want x value, so x is PL by AE. Substitute this x value in this equation of P into x is PL by AE, which is nothing but your strain energy U is equal to half P square L by A. So the strain energy stored in a bar which is subjected to axial compression or axial tension is nothing but P square L by. So what we have done is here first we calculated what is the external work done, and this external work done is equal to the internal strain energy external work. So external work done is nothing but load into displacement. Here, if we have to consider the graph and wherever the hatched portion area under the curve is giving the external work done. So it looks like a triangle. The area just understand here a bar is layer of length L which is subjected to axial force, either it is tensile force or compressive force along the length of the member. When it is subjected to a force of capital P, there will be a deformation. So that deformation we are considering it as X. At load 0, deflection is also 0. Whereas if you keep on increasing the load, there will be an increase in the deflection. So certain load P is applied, the corresponding deflection is X. If you slightly increase the load, delta P, then there is a slight increment of dx. The force, whatever you are considering, it may be compressive force or tensile force. Now, we have to calculate what is the external work that is done. We know that work is nothing but force displacement, or here if I say deformation or displacement, that is either rotation or deflection. So here, so here we have to consider the graph. What is happening here? If you understand the graph, the load is gradually increased to certain value. So this is the one which is coming from the portion. The area under the curve can be considered as your work done. So the area is this is x, this value is p. Why? Because here this is p. So half p into x is considered as external work done, which is to be equated with the internal energy. So internal energy U is equal to half p into x. In our basic strength of materials, we know that what is the meaning of x? That is nothing but PL by AE. So that is PL by AE. If you substitute it, you get the strain energy U is nothing but P squared L by 2 AE for axial loading. So in case of axial loading, that is nothing but the strain energy stored is nothing but P square L by 2 AE. This is when the cross section of the bar is uniform. Along the length of the bar, the area is capital A. Now, if the cross-sectional area is varying, then how to calculate? So just note down the additional point for this. With varying cross-sectional area of bars, with varying cross-sectional area of bar, U is to be considered as what we will consider is we will consider a small element and a small element will be integrated. So here L is nothing but the length of the member. So here just see this one. This is 0 to L square into dx by 2 into ax into e. Ax is nothing but the cross-sectional area. So this is applicable for a bar with the varying cross-sectional area like this. Varying cross-sectional like this. At any cross-section from a distance of x, the cross-sectional area is Ax. So note down this one. With the varying cross-sectional area of the bar, the strain energy is nothing but p squared by 2ax into e. This is integration from 0 to L into ax. So this is the length of the member. So we are integrating from 0 to L. And a small element at additions of dx is considered. This is called as a small element of x. Now, let us go to the next one, strain energy due to bending. Now, the next point, strain energy due to bending. That means when a beam is subjected to bending, then what is the energy that is stored in the body that is to be calculated? Now, see this one. A bar is there. Just please first listen, then you can write down. I will explain you this page. Now, this is the bar, and this bar is of length L. So to get bending, what is to be happening here? The moments are to be applied at the ends. So the moment is applied at the ends. So due to this, what will happen? The beam will get curvature like this. So the beam will get curvature like this. Now, you might have studied from the basics of frictional formula, the same thing we are doing here. Here, this is radius r. This is the neutral axis. This is the neutral axis. So consider a small element. These are here. First, you listen, then you will understand the concept. We are considering a small element with along the curvature, the length is ds. Along the curvature, the length is dx. Now it is making an angle with respect to the horizontal as d theta. The same angle will be made at the origin. This is also d theta. Now the horizontal distance, this will be referred as dx, and the vertical one will be referred as. We are considering a small element of length ds along the curvature, and this curvature, what it is doing, the small element is like this. Small element is in the curvature, it is like this, and this distance is ds. Now with respect to horizontal, this is making angle of d theta, and the vertical distance is, this is vertical one, this is horizontal one. This is considered as dx, and this vertical one is considered as dy. The angle is nothing but d theta. So I can write down this as d theta is nothing but dy by dx, opposite side by adjacent side, d theta. Whereas coming to here, if you understand, r is the radius and angle made by this one is d theta. So the arc length ds is nothing but r into d theta. ds is nothing but r into d theta. What we are doing, we considered an element, a beam of length L, which is subjected to a bending at the ends. Now the length of the member, this is L, and this is the origin point. A small element of ds is considered. The small element is making an angle of d theta with respect to horizontal, where d theta is dy by dx, and the small element ds length, arc length, is nothing but radius multiplied with the angle. You will get r into d theta. Now we will write down the strain energy in small element of length dx. Strain energy in small element of length dx is, we know that u is nothing but internal work done is equal to external work done. So the strain energy u is nothing but of into, here moment is applying, moment into rotation or force into deflection. Here m into theta. But we are considering for a small element. So dou u is equal to half into m into dou theta or d theta. So here dou u is nothing but m into, here our d theta is nothing but ds by r. Dou u is equal to half into m into ds by r. We know that as per flexural formula, m by I is equal to e by r, or 1 by r is equal to m by ei. Yes or not? 1 by r we call it as curvature, that is nothing but m by ei. So substitute here, m into 1 by r is nothing but m by ei into ds, which is nothing but 2u. which is half squared by EI into ds. So for a small element that is rho u, but to get u, that is nothing but integration of 0 to L rho u, that is integration of 0 to L into m squared by 2 EI. So the strain energy stored for if bending due to bending is nothing but integration of 0 to L m square by 2 EI into ds. So we write down here. Please keep heading strain energy due to bending. And here write down any action which causes stress in a body, any action which causes stress in a body induces strain energy. Induces strain energy. Consider a beam of length L subjected to bending. Subjected to bending. Draw the beam of length L which is subjected to bending due to moments and the curvature. We know that 1 by R curvature is nothing but M by EI. So this is the derivation for the strain energy due to bending. Right. So what we have understood is when a beam is subjected to bending and within the elastic limit, it can regain its original position. The energy stored due to the bending is calculated as integration of 0 to L m squared by 2 EI into ds. ds is nothing but along the length of the member. It is not horizontal length. It is along the length of the member. So how to calculate uh, the deflection at the point of application of single load? For example, a single load is applied. So what is the deflection at the point of application of single load? Just note down. Deflection at the point of application of single load. So here a load is applied. So wherever the load is applied, at that point, how to calculate the deflection? So to calculate that one, what we will do is internal work done is equal to external work done. So internal work done is nothing but strain energy, which is equal to external work done half into, I will calculate this as a load. I am considering it as W and a deflection as delta of W. So delta is nothing but 2U by W. This is the formula to calculate the deflection at the point of application of single load. So you can represent this W as P also. As P also, it is load, the value load. Now, what is meant by U here? So what is meant by U here? You have just U is nothing but sigma P square L by 2. What is the meaning of this one? I will explain you. Don't get confused. Here U is nothing but summation of P square L by 2AE. Now let us go back to the first one, strain energies that is due to axial force. Now see, at each individual member, the strain energy is nothing but P square L by 2AE. If the bar is uniform cross section, then the strain energy for each bar is nothing but P square L by 2. Now we have a truss or a frame. For a frame, and there is at one point a load is acting. So the meaning is nothing but, for example, a truss is there. Something like that, a truss is there like this. So this is also applicable for pin jointed perfect frames. Here a load is acting, something like W. And I would like to calculate what is the deflection at this point. This is A, then this is B, this is C, and D. Now, what is how to calculate the deflection delta C? So to calculate deflection delta C, the formula is nothing but 2U by W. How you got? By making internal work done is equal to. So what is the meaning of U? U is nothing but the strain energy stored in the entire frame. So how to get it? Summation of each individual strain energies, which is nothing but, as this frame is pin jointed perfect frame, this pin jointed perfect frame will be subjected to only axial forces. And these frames will be subjected to axial forces. They will be subjected to either tension or compression. They will not be subjected to any bending. That's why the strain energy stored in each bar element is P squared L by 2 AE. You know, AE, what we call this AE? AE is called as axial rigidity. AE is called as axial rigidity. Here, if I call it as this EI, EI is called as flexural rigidity. Now, get back to this. So, if you the strain energy for the entire frame will be calculated using summation of P square L by 2 AE. From this, we will get 2U by W, which is nothing but deflection at the point of application of